Imagine an AI that can see, read, and even hear just like humans. That's the power of large multimodal models, the next evolution of artificial intelligence. But how do they actually work? What are the core techniques that allow them to integrate and process multiple types of data? Hi everyone, this is Tanguy. Welcome to this video about large multimodal models and multimodal foundation models, an overview and the methods used in those fields. In this video, we'll take a deep dive into the key training strategies for these models and illustrate how they function at a fundamental level. Let's dive in. Before we dive into the methods behind these models, let's define our key terms. A large multimodal model, or LMM, is an AI system that processes and integrates multiple types of input such as text, images, audio, and video into a single framework. These models aim to perform a variety of tasks by combining different data streams to form a richer understanding of the information they process. A multimodal foundation model, or MFM, is a specialized LMM that serves as a general-purpose base model. Unlike models that are designed for one specific multimodal task, MFMs can be fine-tuned for various multimodal applications, such as image generation, visual understanding, or real-time interaction. In this video, we will mainly focus on language vision multimodal models, because they are the most common ones that exist. Three major challenges that multimodal models aim to solve. First, visual understanding, how models extract semantic meaning from images. Second, visual generation, how AI can create new images or videos from text descriptions. And third, general-purpose interfaces show we design models that unify multiple modalities into a coherent AI system. To truly understand these models, we need to look at the methods used to train them. Each of these challenges requires different learning techniques, and that's exactly what we'll explore next. How does AI understand images? Visual understanding models focus on extracting meaningful information from images by using different levels of supervision during training. One of the most common methods is supervised learning, where a model is trained using a dataset of images with predefined labels. During training, the model learns to associate specific patterns in the image data with corresponding labels, enabling it to recognize similar patterns in new images. However, this approach requires large amounts of manually labeled data, which is both costly and time-consuming to produce. To reduce dependence on labeled data, researchers have developed contrastive learning techniques. In contrastive learning, the model is trained by comparing pairs of data points. It learns to bring similar items closer together in its internal representation space, while pushing dissimilar items farther apart. For example, CLIP, developed by OpenAI, aligns images with textual descriptions by training on massive datasets of image-text pairs, enabling zero-shot classification. Another major method used in visual understanding is self-supervised learning, where the model learns by solving pretext tasks without requiring human-labeled data. One example of this is masked image modeling, MIM, where random parts of an image are hidden, and the model must learn to reconstruct the missing portions. This forces the AI to develop a strong internal understanding of image structures, improving its ability to generalize to new data. Visual generation models take input data, such as text descriptions, and produce entirely new images or videos. The process of training these models requires powerful generative techniques that can synthesize realistic outputs. One of the most effective methods for training visual generation models is diffusion modeling. In this approach, the model starts with an image that has been heavily corrupted with noise, and its task is to gradually remove the noise step by step until a clear and structured image emerges. By learning this process of denoising, the model can generate entirely new images from random noise. Another common approach is transformer-based architectures. These models use self-attention mechanisms to process input sequences and generate coherent outputs. Unlike older architectures, transformers can model long-range dependencies between elements in an image, allowing them to generate highly detailed and structured visual content from textual descriptions. Finally, generative adversarial networks, or GANs, offer another way to train visual generation models. A GAN consists of two networks, a generator and a discriminator. The generator creates images, while the discriminator evaluates whether the generated image is real or fake. Over time, the generator improves by learning how to fool the discriminator, resulting in highly realistic image outputs. Beyond understanding and generating images, Some models aim to become general-purpose multimodal assistants, capable of reasoning across different types of input. These models require specialized training methods to unify multiple modalities into a single system. One approach is to unify vision models without relying on large language models. Perceivers, developed by DeepMind, use a single transformer-based architecture to process multiple input types such as images and video without needing separate encoders for each modality. This is achieved by mapping different modalities into a shared latent space, where they can be compared and processed together. Another approach focuses on training multimodal large language models. Flamingo, for instance, extends traditional language models by incorporating vision encoders so they can process both text and images in a single workflow. The key challenge here is aligning the representations of different modalities so that they can be understood in a unified manner. This is often done through instruction tuning, where the model is fine-tuned to follow prompts that mix text and image-based queries. Finally, there is the method of chaining several tools with language models. It is like using the LLM as an orchestra conductor to coordinate each tool and use the proper ones when they are needed. So, unlike the previous model, this agent is modular and uses the LLM to communicate which every module. Some models, like MMReaked, take a modular approach, where a large language model acts as the coordinator, selecting the right expert models for different tasks. This allows for greater flexibility and scalability in multimodal AI systems. The next wave of AI advancements will focus on three key areas. First, unifying different tasks, bringing together generation, understanding, and reasoning into a single, seamless model. Second, improving tool chaining, making it easier to integrate multiple specialized AI components. And third, enhancing human alignment using reinforcement learning to fine-tune AI for real-world applications. The long-term goal is to create generalist AI agents that can navigate and interact with the world in a human-like way, seamlessly integrating vision, speech, and actions. And we are done. We've covered the key training methods behind visual understanding, visual generation, and general-purpose multimodal AI systems. I hope you liked this video and learnt a lot about large multimodal models and multimodal foundation models methods. Thanks for watching.